Go ahead and chat me your first and last name. Looks like everybody is doing that, so thank you for that. Anybody have any questions? Go ahead and ask. I'm here for you.
Uh, did you get my email? I sent it on Saturday.
Yeah, well, let me double check. Who's this speaking?
Colin?
Yes, you're the one that asked about using my exam time. Is that correct?
Yeah, I was trying to figure out what if um it was confused on whether or not we had to call the station or if we had to show up in person.
Oh, gotcha. Yeah, so I made that up today. What class are you with, Colin? Are you in PHY 241 or 100, or you're in 241, right?
241.
Okay,
Yeah.
gotcha. So, actually, no, I don't recall getting your email. I was thinking of someone else, evidently. Sorry about that. You want to explain to me, or just you want me to check it afterwards? I'm sure I just missed it somehow
Uh,
or other.
I was just wanted to know if we still had to call the testing center,
Oh,
or are we
gotcha.
showing up to you in person? As well as I wanted to check which chapters the second uh, face to face was actually covering, because the first one covered 5 chapters and we just did chapter 8. So
Yes. Let me double check on that just to make sure I don't want to quote the wrong answer to you. So I am going to, oh, can't go there. Oh, can't go there. Okay, it looks like I can't do a darn thing. All right, let me pull this open. I just, like I said, I don't want to state it, and then because I've got so many classes I'm teaching right now, I don't know which chapters are what, and I'm teaching multiple ones that are like 241 material and multiple ones that are like 242 material. So I've just pulled it open now. Hopefully, that's not it. There it is. Okay. So yes, what I've done is I've made the next online test will be up through chapter 8. So it's 1 through 8. Ostensibly it's mostly on 6, 7 and 8, but like I said, all our tests are comprehensive. You are welcome to take it this Wednesday. And I might even, because I've allowed you guys to take it from technically today until a week from today, which is Wednesday. So I would allow you to take it with my lab this Wednesday because that's when they're actually taking their 241 test. If you really want, in principle, I could do it the following Wednesday as well, but it wouldn't be necessarily a good testing environment because you'd be taking it during either a lecture or during a lab, both of which are not necessarily ideal because I'll be talking about stuff and it might not be quiet for you. But you can still take it at the testing center on Wednesday as well if you'd like.
okay.
Did that answer everything, Colin? I'm sorry. I thought I had answered all my emails, so I must have missed yours somehow or other.
Um, I
You think
I
I've
just
met?
wanted to make sure, like, for the face to face, like, does it so we can either show up to your lab or do the testing center?
Yes, show up to my lab this Wednesday. I can give you the specific time, so you could, for instance, come Wednesday at 9:30 a.m. I would probably say it'd be better for you to show up at least 10:15, something like that would be best. But you could do it at that time. You could also do it again at 12:30, and you could do it also again at about quarter to 2. So any of those three would be okay. If you let me know which ones, that would be ideal. But it's not critical that I know exactly which one you're going to. Just tell me roughly what time, so I'll make sure I can do it. But you are welcome to that, and you're welcome to use any testing center on any TCC campus. I've already set it up with them. They know they expect you sometime today up till all day Wednesday. Not two
Like,
days from now, but a week from then.
okay.
All right.
I'll see what I can do just because I do have work.
Yeah. Like that's why I said I tried to make it more than a week because I knew you specifically, and then some other people have very specific time constraints. That's why I tried to give you multiple options and give you more than just the normal 7 days.
All right. Thank you.
Thanks for sticking to it, Colin. I'm sorry I didn't get a chance to catch your email. Anybody else have any questions? I know somebody emailed me a question about showing up on Wednesday. That's who I thought was Colin was, but like I said, I didn't know that I didn't recognize his voice and didn't see which name was talking. But anyways, that is an option for you guys if you want to. Just let me know whether you're coming this Wednesday or next Wednesday. This Wednesday is really what's intended, but since I made it an extra long time, I can actually do it the other way as well. I can let you take it, but like I said, it will not be an ideal environment. You're probably going to be taking it while I lecture or while I administer a lab. Both cases that could be a loud situation. So if you have any difficulties working in that kind of environment, I wouldn't recommend taking it a week from Wednesday, but rather just Wednesday. And if you want to take it a week from Wednesday, you're welcome to, but you're going to have to make an appointment at the testing center. But you also have, tomorrow, Wednesday, Thursday, Friday. Testing centers do have Saturday hours. I don't think that any of them have Sunday hours. But then you got Monday, Tuesday, and Wednesday again of the following week.
Oh, I did have one other thing. Do you know why chapter 7 and 8's homework haven't been showing up on Canvas even when you enter through the Canvas site?
No, that should be. I even checked it just this weekend. Let me pull that up real quick because that's certainly something that you need access to. Well, actually, yeah, let me pull this up. I'll pull that up real quick and double check and see what happened. It might have been something where I clicked on it and accidentally double clicked, and that sometimes will make it unpublished. But as far as I knew, it was all working.
Yeah, my chapter 7 and 8 homework hasn't come through for some reason.
It's probably not yours then. It's probably everybody's. I can't imagine a scenario in which yours does it. Let's see.
Same here.
Oh, I see. Wow, that's weird. I changed this date like 2 weeks ago, and it's showing 10/26 was the date on chapter 7. Uh, Maybe that was the problem that it closed early. I'll tell you what I'm going to do. 7 and 8 are showing up within your mastering course, but they're showing chapter 7 is showing to be due 10/26, which was last night. What I will do, I'm going to go ahead and push that till Sunday, even though that's way late. But I'd rather you guys get a chance to get it done because that's obviously going to help you with this test. And then chapter 8 is technically due on the 28th. It is here. It should be here, but you're not seeing it on your side. And I think Jaden
Yeah,
said she wasn't either.
no, the chapter 7's fully done. Chapter 8 is mostly done. I want to ask after class about a couple questions, but I've gone through them. There should be grades on there, but it's just not
Oh,
showing
that's what
up.
you're saying. Okay, got it. That makes me feel a lot better. Cool.
Yeah,
Uh,
like just the grades aren't showing up is the
Gotcha.
thing.
I know exactly what that problem is, and that's a lot easier problem. Let me go back to this other screen. I
So
did push the date back. Yeah, Jaden. All right, I
I
think that
said
was you.
that mine are resetting. I don't know if you've noticed, but mine are saying zeros and missings, and I don't know what's going on. I do my homework every weekend.
Yeah, oddly enough, I just looked, and it's not showing that 7 and 8 were doing the weird things that I suspected it's doing, but they might have had a little bit of problem. Let me pull up the grade book within Canvas and see what it looks like versus the grade book within uh, MyLab and mastering. It doesn't matter. Don't worry. As long as your grade's showing on the mastering side, then it will show up here. If I'm looking at it, uh,
I'm not getting any of that. Every time I do, like, I'll finish a chapter, and I think this has been happening for quite a bit because I looked at my grade recently,
mhm.
and it tanked horribly. Now, I understand I didn't do the best on my exam, and I'm perfectly okay with that because I've been studying. But um, I've checked, and I'll go back the next day, and it'll say I didn't do anything. I don't know
Gotcha.
what's going on.
Yeah, I do see several zeros here. Now I don't see zeros for yours, Colin, but these could have been if they don't show up on my side after a certain date, I put a zero in them so the grade book will start counting it because otherwise students won't get scared enough about their grade, and that's a whole nother problem. So I can always erase the zeros on here and just see if it refills with the appropriate grade. So I'll do that right afterwards, Jaden. And Jaden's not the only one by any stretch of the imagination. I got several people that have zeros marked for these, but it does look like all the grades are coming to my grade book other than possibly those zeros that may not have been correct, but that could have been because I put in a zero just because they didn't come in time or quote unquote what I thought was in time. So,
So should I redo it then?
no, not if they're showing on the other side, and that allows me to check this real quick. I'm going to pull
And
this up. Go ahead.
you do see the grades I got for chapter 7 and 8 so far?
Let's see, chapter 7 and 8. This is Colin talking, right?
Yeah.
Yes. So let's look at, I see chapter. Ooh, oh, just lost everything. Went somewhere else. Okay, here I am. Chapter 7. No, okay. That's weird. Why is this
Yeah,
column not
because
even
I
showing?
I finished chapter 7 last week
And
and
actually,
chapter
no
8
one
I'm
has
going
it.
to.
Yeah, I've got to call mastering on that. So yeah, it looks like 7 and 8, conceptual and homework, are both all missing. So they're just not coming here. But if you've got them in the other side, don't worry about redoing it. That's not your
All right.
problem at all. That's all my problem or mastering's problem. And
Okay.
it does look like your grades are fine within the grade book for chapter, yeah, for chapter 8 and chapter 7. You're golden on that one. I do see a couple missing on some of those other people that had zeros, but we can negotiate that situation as well a little later. So, yeah, if you didn't do them at all, I would say, I mean, if it's showing zero, I would try to contact my lab and mastering and say, hey, I did these on such and such a dates. Where are my homeworks? And they should be able to, because they actually don't only monitor what your scores are, they can actually tell exactly what time of day you've been there. They can tell what computer signed in with it, signed into the system, how long you spent, all that good stuff, exactly how much time you spent on each question. So if you come to them and say, "Hey, I did this on chapter 7 on," and you don't even have to say what day, they can look into chapter 7 and see exactly what days you've logged in. So by all means, feel free to contact them. If it's not showing on the mastering side, there's nothing I can do. You've got to help. You've got to get mastering help on that one. But if it's showing in mastering and not showing on my grade book, that's not your problem. That's a problem that I've got to fix, and that's a problem that mastering physics has got to fix. I can and I will. What ultimately happens if they don't get it done by the end of the semester, then I manually put them in, and sometimes I'll even do it early just so you guys will know what's going on. But that's the main thing that's going on with that. Anybody? Bree said theirs aren't going through either, or Braylana, sorry. I just saw the BRE. So yeah, I will look into this and get all that fixed. But like I said, it's probably something where I've got to call mastering and find out what's going on. But most of them are not zeros. It doesn't look like nearly as many zeros are on uh, this side as I expected. So it does seem to be a handshaking problem between mastering and the grade book. However, there are some zeros within the mastering grade book, and that makes me concerned that that they weren't either done or they were done and somehow didn't get recorded. If they didn't get recorded, that's something that mastering's gotta address, and I hope it's not a problem. If they determine that you did it and that you should be getting credit, then they'll write me a letter accordingly, and I'll do what I can to make the grades right. Okay?
Thank you.
You're welcome. Anybody else have any questions? All right. Well, we have finished chapter 8, and I thought I hadn't even posted the last video from chapter 8. But I looked at it and realized I did, but I put the wrong date on it. That's what was confusing. So if you found two videos for October 20th, one of those was October 20th, and the other one was October 22nd. The 22nd has now been fixed to say the 22nd again, and is therefore working properly. We are now going into chapter 9, which is the chapter on linear momentum. And with that comes a whole nother law and actually a better version of Newton's second law. So, what I want to do is go ahead and get started on that. Does anybody have any other questions before I get started? This is a time for you to ask questions on chapter 8 material, or like y'all done now about the assignments and stuff, you can ask that as well.
Yeah, I have a question.
Go
It'll be
for it.
pretty quick. In the homework for Chapter 8 conceptual, asked about a zero level for potential energy. I
Right.
was wondering if we could just normally just use the floor as a zero level, or if there's like any like why would you use anything else is my question, really.
Yeah, so it turns out like if you've ever been to somewhere like Busch Gardens, for instance, you know that when you get on the Busch Gardens ride, you sort of walk along this little path until you finally get up to the car. And what you'd find is that's sort of the low level of the I mean of the track that's going to make the Loch Ness Monster say. But then as soon as you leave it, the Loch Ness Monster goes up a hill and then shoots way down. And then at one point, you're actually doing loops and you're coming just a few feet off the water. So it's not unusual for you to call the initial part where you got on the roller coaster, you call that height zero. And that's perfectly fine. But what that means is when you get to that part that's lower than it, then that height will be negative, and that's okay too. What you might do is you might be thinking like you and say, well, that's really stupid. I should probably take the zero to be the lowest point on the roller coaster. So then you go find the lowest point on the roller coaster, and it's that part where it's right above the water. And you say, okay, I'm going to call that y equals zero. But then another person might come by and say, why would you do that? That's not the ground. The ground is water level. But the point of it all is that, the parts that are relevant about potential energy are not the value of the potential energy, but rather the difference or the change in the potential energy. So if you imagine that, for instance, you took the ground to be zero and someone else took, 3 meters above that, then you're always going to be off by m times g times 3 meters. But both of you are going to have m times g times 3 meters in that. So when you subtract it, final minus initial, the 3 meters comes in positive in one case and the 3 meters comes in negative in the other case, so it cancels out. That's the whole point that they're trying to let you see, and that was also the whole point of the example where they had the very first example with the roller coaster, where they said, "What is the change in potential energy from point two to point three using one as the relative point, basically?" And then they did it again using three as the relevant point. So there's nothing wrong with using any height you want. It's perfectly reasonable if you're on the second floor to call the ground of the second floor y equals zero. And it's perfectly reasonable if you're on the first floor thinking about somebody on the second floor, you could use the y equals zero at the bottom of the first floor. You could even use it as y equals zero as the ground outside, which might even be lower or even higher than the height of the ground inside the first floor. It doesn't matter at all because ultimately that extra quantity will be added and subtracted and therefore never come into play. Does that help you,
Yeah,
Ryan?
that's perfect. One last quick question. For friction, like the workout and the
Mm-hmm.
conservation of energy, um, that's the conservative force on the, I guess, the right side of the equation. Like, what's the energy loss come into effect? Is
So
that not friction or is that something else
I,
entirely?
I I put that over there to deal with friction. That's why the E loss is in the far right side. But it could be E loss for anything. For instance, some people say, "Hey, if you're going to compress the spring's stealing some energy from you," so they'd call 1/2 kx squared E loss, and that's perfectly okay. The main thing is you want to make sure you count every loss of energy, and it doesn't matter which term you put it in as long as you count it and you only count it once. So yeah, you could say E loss would be 1/2 kx squared, but I originally put it there for friction force times the distance.
Okay, thank you.
No problem. And yeah, and not only that, it's perfectly reasonable when you say E loss, that could actually be four different terms all put in E loss, or it could be one term in E loss, or you could have two workouts and two E losses. That's all acceptable as well. The big thing is don't count anything twice and make sure you count everything at least once. Or I shouldn't say at least, exactly once. Anybody else? you'll see the actual practice of it is a lot easier than the explanation of conservation of energy. When you start doing your practice test, which the homework's way is considerably harder than the practice test and therefore considerably harder than the test, but but that's the way it should be. So when you start doing the practice test, I think you'll be a little nervous, while you're doing your homework, but then you get to the practice test and your nerves will go down a little bit because you're like, oh, wow, this is a lot easier than I expected. Anyone else? All right. Well, we're going to go ahead. I'm going to start by sharing my screen, my iPad screen with you guys, and we are doing chapter 9. And remember, as always, there's a chapter opening question, and you should always do that, of course. And in this case, I also want to point out that chapter 9 has very specific sections. And like always, I generally skip the asterisk sections. So there'll be subsections within each chapter, and they start off with a little asterisk by the subsection's name unless I explicitly tell you otherwise, or you explicitly see me working problems or you see me explicitly solving problems from that section, then you can assume that section will be omitted. But it's omitted only in the sense that I'm not going to ask you any questions about it on a test. I'm not going to have you make up examples, nor am I going to make up examples from that subsection and put it on your test. There may be some questions that refer to it in your homework, and you might even occasionally see something in the practice test. I've tried to remove all those from the practice test, but just know that generally speaking, you're not going to be required to do it. You should read it because it makes you educated and more understanding of the world. But again, I'm not going to be testing you on it. So when I look at the chapter on linear momentum, of course, it has a couple pool balls on it, and the subsections are 9.1, momentum and its relation to force, 9.2, conservation of momentum, 9.3, collision and impulse, 9.4, conservation of energy and momentum in collisions, 9.5 is elastic collisions in one dimension, 9.6 is inelastic collisions, 9.7 is collisions in 2 and 3 dimensions, and then we get to what seems like an entirely different scenario, but oddly enough turns out to be mathematically exactly equivalent, and that is the center of mass. I teach you how to calculate a center of mass, and what you'll find out is when we conserve momentum, linear momentum, it gives you the exact same results if you take into consideration that momentum is conserved only when the net force on the system is zero. And then if you learn about center of mass, you realize when the net force acting on the system is zero, then the center of mass either can't move or it moves at a constant rate. And because of that, any problem you solve with conservation of momentum, you can also solve by treating it as a center of mass problem. So we do talk about how to calculate center of mass, and then we talk about center of mass and translational motion, because right now we're looking at, instead of when I throw, for instance, a pin, we don't treat this pin as if it's a pin. We treat it like it's a point object so that it just flies like this. In reality, when I throw this pin, it does this sort of spinning and stuff. So how do you treat that from a physics standpoint? Well, you treat it like its center of mass is going to obey the principles that we learned about when we were treating single particles. In other words, the center of mass of the ink pen is going to be the thing that follows the parabolic path in projectile motion. But then once you learn rotational motion, you'll learn that there's a spot on this that you could just choose on this pin some distance away from the center of mass, and you can just follow that in time. And there's another set of equations that'll tell you not only where the center of mass is, but what the orientation of this object is. That's part of why we cover the center of mass, because once you get the center of mass done, then you can use the center of mass coupled with the rotational motion and figure out not only, for instance, whether this center of mass of this pin is going to make a parabolic trajectory. You can even figure out what is the orientation of the pin when it hits the ground, so you could make up for the limited or slightly less hang time that you get as a result of the pin being in this position, and therefore this part hitting the ground before the center of mass does. So that's where we're going with this. Hopefully that helps you. And again, like I said, don't forget to do your chapter opening question. I'm going to start off with section 9.1, and specifically, I'm going to tell you what Newton gave us. So, Newton did not give us the summation of forces is equal to mass times acceleration. That's what we've been using. The summation of the forces is equal to mass times acceleration. And we've been using that predominantly, but in fact, it's not completely right to do that because we've been treating A as if it were a constant. And a lot of times when we're solving these problems, it is a constant. But that's not necessarily the case. In fact, the way we should treat it, even in this scenario, is the summation of the forces is equal to m dv dt. The point being that Newton's second law is a differential equation. And if you're attempting to solve for velocity, it's a first order differential equation, meaning the highest order derivative you have is first order. If it's an attempt to solve for the position, which is x of t, then it becomes m. If I wanted to, I could either use a vector called x vector. That is a vector that points to any arbitrary point in space, but you can see the problem with that. People will think, oh, he means the x-axis. So what we normally do is instead use r in place of x, in which case this becomes d2r over dt squared, where r is a position vector. But now you see it's a second order derivative. So Newton's second law, even in the form that we've been using, which is quote unquote the training wheel version in some sense, that is still a second order differential equation. And that's what you have to solve if you're not fortunate enough to have a problem that deals with constant acceleration. If you have a problem that doesn't have constant acceleration, then you have to do it as a differential equation. That being said, it's not strictly correct. This is not the correct version of Newton's second law of motion. It's correct for a lot of problems, but it's actually missing some terms because what Newton actually said was the summation of the forces. Now, remember, I told you vectors hadn't been invented yet, so none of this vector stuff was in existence when Newton wrote it. But he sort of understood exactly. Well, I shouldn't say sort of. He's friggin' Newton, so yes, of course he understood it. But he did it in such a way that we could understand, and we were able to generate vectors by studying his stuff. But what he said was the net force acting on a system was equal to dp over dt, where p is defined to be the momentum. Now, that is the equation, in some sense, that is the equation for a particle, okay? But in reality, as we told you before, for instance, when we did the three boxes tied together, you can actually use Newton's law, Newton's first, second, and third law for systems. In other words, for the three masses tied together, we can treat that as one system, and then you'd have a Newton's second law for that three mass system. You can also have it, for instance, if we look outside, you might see a group of birds, a pack of birds, if you will, flying in V formation. Well, they obey the laws of physics as well. Of course, they've got their own brains and their own ability to generate forces and stuff like that. So they might be a little bit more complicated. But in general, you can still treat them as a system. And when you do that, then the system becomes P is equal to, or I should say, P goes to P total, which equals M1 V1 plus M2 V2 plus dot 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 for however many particles are part of the system. And ultimately, we can even go a little further. Instead of treating it as individual discrete objects like countable, we can actually go further and say that the object is made up of infinitesimal little pieces, and then we'd have to integrate to get it. But the main thing is this net force is equal to dPdt is the full version of Newton's second law. If you think about it that way, then you can see something special. Specifically, the summation of the forces is equal to d by dt, If we're talking about just a particle, that's the derivative of mass times velocity, like that. And of course, that's a product. So the calculus rules tells us that when we take the derivative of a product, we take the derivative of the first factor and we multiply that times the second factor. Plus, we take the first factor and multiply it by the derivative of the second factor. So that is the complete version of Newton's second law, even for a point particle. What you see is this part right here is what we've been focusing on, and it's this term right here that makes that wrong. So if we had an actual mass that was changing as a function of time in any sense, then F equals ma, as we've been using it here, would be wrong by this amount. So this is our new version of Newton's second law, and I'm going to include the P for it being a system as well. And I'm also going to include this just to keep in mind. What you'll see in the rocket equation, basically there's a rocket equation that uses this form. It's a little bit complicated to apply. I skipped that section for you guys because if you're actually going into aeronautical engineering or aerospace engineering, anything like that, you're going to have courses on orbital mechanics, courses like this where you learn basically all the stuff you're going to do to calculate rockets taking off, rockets losing mass, rockets establishing a elliptical orbit, and all that good stuff. So you'll get plenty of time to cover it. I just wanted to point it out that we're going to skip that section for that reason because you'll get a much better understanding of it from them, anyways. Now that we have that, I want to show you a ramification that's really important. I've been telling you guys how when I have a section or a subsection of a chapter that's called something like Newton's law or Newton's first law or the first law of thermodynamics or such and such a principle. When you have a whole subsection or a whole chapter named after something like that, just as a bare minimum in college, you guys need to immediately assume, oh, I better memorize whatever that principle, whatever that law, whatever that equation is. I need to memorize it and have it memorized at the drop of a hat because at any time an instructor could ask you for it on a quiz or on a test, and the instructors think they're just being super, super nice to give you that because that's sort of the bare minimum of what we expect for students to learn when we have something like Newton's law of motion. So I'm getting ready to give you yet another law. Right now, to date, you should know, for instance, Newton's first law of motion and know exactly which one that is. Newton's second law of motion and know exactly which one that is. Newton's third law of motion, know what that is. Newton's universal law of gravitation, not only should you know what that is, you should also know why it's called a universal law of gravitation. I mentioned that when I cover it. That's something you should be able to answer. We also covered Kepler's three laws of planetary motion, so those three you should expect to know as well. So at any point in this semester, now that we've covered all that material, including this one, you should be ready to answer what we think is a simple question like state Newton's second law of motion, state Kepler's third law of planetary motion, or state the conservation of linear momentum, which is what I'm getting ready to show you now. So I just, in that little spiel, I went over all the things that we've learned so far that you definitely need to commit to memory. So you can go back and look at this video and find out for sure what it is. And let me give you the newest one, which is the law of conservation of linear momentum. So if, I should probably write this in a different color. I'm going to write it in purple. If the total force acting on a system is zero, then Newton's second law suggests that dp dt is equal to zero. Everybody see why it suggests that? I said if the summation of forces is equal to zero, then Newton's second law suggests that dp over dt is equal to zero. Everybody see why that's the case? And let me go ahead and open up this chat so in case somebody chats something I don't know. Okay. So notice it's just the two sides of Newton's second law. One side is the summation of forces, which I just set equal to zero. The other side is dp dt, which I just set equal to zero because obviously it was supposed to be equal to the summation of forces. So if dp dt is equal to zero, what do we know about p?
It's also zero.
Close. It's a constant, right? Does that make sense? You see why it would be a constant, but not necessarily zero? Good job, though. I totally appreciate everybody answering, and there's no shame in getting any something quote unquote wrong. But you're very close. It means that the momentum must be a constant. In this case, it's a constant vector. So it's a vector that would have like a constant number times I hat plus a constant number times j hat plus a constant number times k hat. That's the main thing. That this is the law of conservation of linear momentum. Okay, so two things here. You should be able to state the law of conservation of energy, or excuse me, the law of conservation of linear momentum, but you should also be able to state under what conditions the law of conservation of linear momentum is valid. And what that is what it says right here. If the summation of the forces acting on the system is zero, then linear momentum will be conserved. So that's the key part that we're trying to understand here, and that's what we're going to be working on. But first, now that I've sort of given that all that information to you, we need to do some work with actual calculations of momentum and some other quantities, like we're going to call something called an impulse, which turns out to be the change in momentum. But just like the dot product had two different formulas for calculating the dot product, the impulse will have two different formulas you can use for calculating the impulse. So I want to make sure we are all doing that. So if I turn in my book and look to the first example, we'll see example 9.1. I think this is Roger Federer. It looks like him. I think that's what he looks like, if I remember correctly. It's been a while since I watched Roger Federer, but that looks like him. It says for a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second, which is about 120 miles per hour. If the ball has a mass of 0.060 kilograms, and is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. And would this force be large enough to lift a 70 kilogram person? Okay. So what we're given is the velocity. So I'll call it V final because I know we're imagining the ball initially sitting perfectly still, and then the racket's going to hit it, and then the ball is going to take off with some final velocity. That final velocity is 55 meters per second. I know the mass of the ball is 0.060 kilograms, which is basically 60 grams. When you're in a sporting industry, for instance, they'll have some guidelines like it has to be 60 plus or minus point or 60 plus or minus 1 or 2 grams or something like that. So it could in principle be 59.8 or it could be 62 point or 60.2 or something like that. But that's the kind of minutia you have to get into when you're actually dealing with the complexities of sports, especially once money gets involved, because obviously you could game the system, not unlike the horrible, horrible Patriots did. Bad Patriots. Hate them. Anyways, of course, you can pick on me as you want because I am a Commanders fan. Uh, so, yeah, we've got nothing to be proud of at this point. Delta T is the amount of time that the racket will be in contact with the ball, and that's going to be 4 × 10⁻³ seconds because they said milliseconds, and we generally use the base units. Okay. So what they want to know is A, the average force, and then in B, how does the average force compare to to weight of a 70 kilogram person. Now, to me, anybody at 70 kilograms, I assume they're going to be a kid, but that's just because I'm a fatty. So it might not be true for most people. There's a lot of normal people walking around the world that actually weigh 70 kilograms. I just don't remember being that since I was in sixth grade. Uh, now, we know for this solution is the summation of the forces is equal to dp dt. If I reflect for a second, we can realize that really, if you're examining over a time interval of like 4 milliseconds, the ball's pretty much going to go in a straight line in that little brief period of time. Okay, with that in mind, we can just treat this vector problem as a one-dimensional vector problem. So I don't even have to worry about the vector symbols anymore. And it's just a matter of calling one direction positive, the other direction negative. Not only that, if you're thinking about the tennis ball and the racket hitting it, at that time, there is no other force that even matters even a little bit, because the force that is being applied to the ball from the racket is so much bigger than the weight of the ball. It's so much bigger than any air resistance. It's bigger than any kind of friction you're going to get. So really, that summation of forces is completely overwhelmed by the force of the racket. So I'm going to go ahead and say now that the average force of the racket, which I'm just going to call F bar sub R, is approximately equal to, since I said average, I'm sort of doing the backwards thing that we did when I introduced the average velocity. I said the average velocity would be delta x over delta t, and then I converted that from the average to the instantaneous by considering the limit as delta t approaches zero. In this case, I'm starting with the instantaneous force, which would be dp dt, and I'm going back to getting rid of that limit, and I'm calling it the average. So this average is just going to be delta P over delta T, and I'm not going to worry about any signs. There's an obvious potential to come out negative and stuff like that. All I care about is the magnitude. So with that in mind, I'm also going to make use of the fact that weight is equal to mg, because I need to compare this force that comes out to the weight of a 70 kilogram person. So, so here we start with part A. We're going to say F average for the racket. Actually, I meant to write an average there, not a arrow. For the racket is equal to delta P over delta T. And delta, this triangle always means final minus initial unless I explicitly tell you otherwise. So that means P final minus P initial over delta T. The P final would be 0.060 kilograms times 55 meters per second minus zero, because the initial velocity is zero, divided by 4 times 10 to the negative third seconds. When I do this math, 0.06 times 55 gives me 3.3 kilograms meters per second, which is the units of momentum. Notice that's kilogram meters per second. You could also notice that is a Newton second. So a Newton second is another unit of momentum. I should put that over here. So it's also equal to Newton second. But that 3.3 kilogram meters per second divided by 4 times 10 to the negative third seconds, 4 times 10 to the negative third, that gives me 825 newtons. So the average racket force is 825 newtons. I should point out to you guys, we sort of have a feel for this already, but 1 pound is about 4.45 newtons.
I'm sorry for
Go
the
ahead.
kilograms times meters. What was that? Is that a second under there? I can't tell by the.
Yeah, that's a S right here, and that's a S right
Okay.
here as well.
The G was messing with. I couldn't tell what it was. Thank you.
Yeah, I got you. No problem. So just to remind you, 1 pound is about 4.45 newtons, and in fact, 10 newtons is on the order of 2.25 pounds. So if you want some familiarity with what a newton is, that should give you an idea. Now that we have that, we can go ahead and do part B, which is comparing this 825 newtons to the weight of a 70 kilogram person. So for part B, weight 70 kilograms is equal to M times G, which is 70 kilograms times 9.80 meters per second every second. So if I do that, 70 times 9.8, and I get 686 newtons, which is considerably less than the force, the average force that the racket has on it. So, yes, when you hit a tennis ball, you are hitting it with a significant force. You could literally lift a 70 kilogram person. And of course, 70 kilograms is about 154 pounds. So I might have overplayed my idea of how light a 70 kilogram person is. A 154 pound person is probably what we would call a normal person, at least outside of America. But anyways, anybody have any questions on that? All right. Now let's look to another example. This example is going to be example 9.2. And this one says washing a car, momentum change in force. Water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second. Excuse me, with a speed of 20 meters per second and is aimed at the side of a car, which stops it. That is, we ignore any splashback. What is the force exerted by the car on the water? So this is example 9-2. And what we found out is delta M over delta T. Notice how I just made up a symbol to call this. They gave us a quantity that was 1.5 kilograms per second. So it seemed reasonable to me to call this delta M over delta T. I could have called it M over T. That would have been fine as well, but delta M over delta T lends itself a little easier to apply to F equals delta M over or delta P over delta T. Now, I also have the velocity is equal to 20 meters per second, and what they're asking for is what is the force exerted by the water on the car. So F is equal to question mark. Now, what's going to happen is you can imagine the end of the water hose looking like this, say, and out will come water, and that water is going to be doing something like this. Okay. Now that water is going to run into a wall, basically, which is the car, something like that. And instead of it bouncing back, we're just sort of imagining the water as sort of spreading out along the car and just going dripping down by gravity. Uh, this distance right here could be considered the length, and then the volume, of course, would be the volume of the water would be the area, which might be like pi r squared times the length. So, in principle, when you realize how fast the water is going, a single particle, for instance, is moving at 20 meters per second. So if you looked at this over a time interval of 1 second, it would travel a distance of zero point 0.2 meters. And from that, you could calculate exactly how much water hit it. That's sort of what's going on here. What we're going to do is we're going to take F, which is approximately equal to delta P over delta T, and we're going to realize that that is delta M V over delta T. But in this case, the velocity is not really changing, so we can treat it as if it's V times delta M over delta T. So that's sort of a first order approximation of it. In principle, we'd sort of look back and say, well, what about if the velocity changes a little bit? And we do like that product rule for differentiation or something. But it turns out this is completely sufficient. So what we're going to do is say 20 meters per second times 1.5 kilograms per second. Notice the units turn out to be 20 times 1.5 is obviously 30, and that's kilograms meters per second, which is a Newton. So the average force really is about 30 newtons. Anybody have any questions on that one? Now, what's going to happen, and it would be a little bit more realistic to actually examine conservation of momentum both before it hits the car and after it hits the car. And what you'd find out is, in fact, if the collision of the water molecules with the side of the car is what we call elastic, then the individual molecule will hit the car and bounce off of it with exactly the same speed that it had. So it would come in at 20 meters per second and then bounce off at various angles at 20 meters per second as well. When that's the case, the force turns out to be twice as big in that case, in which case you would get, instead of 30 newtons, you'd get about 60 newtons. But either way, the big point is, yeah, a pressure washer can like break bone and stuff like that. That's actually how my wife met my mother for the first time. Was my mom, and she's a fairly non-traditional woman, and was out doing some of the non-traditional things that she liked to do, like building houses and painting houses and pressure washing houses and stuff like that. And she was out pressure washing, and she just had this bright idea. She was going to lay her pressure washer nozzle right on her top of her shoe. And of course, OSHA approved shoes were slip on Vans, so she just hit herself right in the toe and broke her own toe on it. So be advised, a pressure washer can actually do harm. Anybody have any questions on that? Yeah, we ended up taking my mother to the to the doctors that night, and actually, it was kind of a shame. They found out it was broken, and she needed stitches too. And it turned out that the needle that you stick in someone's foot is way more painful than just about any injury you get on a foot. So keep that in mind if they have to do it. Sometimes it's better to just suck up the pain and deal with the stitches as opposed to that stupid needle. Uh, all right, now we've done that one. Let's move on to the next section, which is conservation of momentum. So I just talked to you about how momentum is conserved. Can anybody remind us right now? Do you remember under what conditions is linear momentum conserved?
Sorry, can you repeat that?
Under what conditions is linear momentum conserved? I'm just asking if anybody remembers. This is something you want to start memorizing now. So the conditions are, as we showed over here, if the summation of the forces on the system is equal to zero. Now, this is only the external forces, because remember, once you say, hey, this collection of particles or this collection of birds or whatever is my system, then the individual force between one particle and another doesn't matter at all. That's an internal force, or between one bird and another, that's an internal force. So it's the summation of the external forces on the system is equal to zero. That's the requirement for linear momentum be conserved. If it's really, really close to zero, you can sort of approximate it as momentum being conserved, but you're technically not correct at that point. So, yes, the condition is the net force acting on the system is zero. Now, just to figure out what momentum would be, if you had n particles, capital N particles, then the momentum before the collision or before some kind of collision or whatever would be m1v1 plus m2v2 plus m3v3 plus dot dot dot. Uh, the momentum afterwards could be written as P final is equal to M1 V1 prime because your book uses prime for final variables. So it's M1 V1 prime plus M2 V2 prime plus dot 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 plus MN VN prime. So that's momentum before, that's momentum after. If the net force acting on the system is zero, then P initial is equal to P final. That's the key. This is conservation of linear momentum. So the only condition that's required for momentum to be conserved is the summation of the external forces adds to give you zero. So that's the key point there. I'd already made it previously. It has some really big sentences like when the net external force on a system of objects is zero, the total momentum of the system remains constant, or the total momentum of an isolated system of objects remains constant. So let's look at a typical example, and this is a very easy one. This is example 9.3. And it's about train cars. It says a 10,000 kilogram railroad car, A, traveling at speed 8.0 meters per second, strikes an identical car, B, at rest. If the cars lock together as a result of the collision, what is their common speed just afterward? So MA is equal to MB, and since they're the same, you might as well just call them M. That's going to be 10,000 kilograms. VA, notice this is the initial, so I don't put a prime on it. And notice because these trains are trains, they're on a railroad track, and therefore they're inherently one-dimensional motion. Even if that train track curves, you can still keep track of how far they're gone using just one variable, the length from where they started to the length to where they are. So it's always going to be one dimensional on a railroad track. In this case, it's going to be 8.0 meters per second. Now, the fact that I called that positive means if our train is moving to the right, then evidently anything moving to the right will be the positive direction. And what we're wanted to find out is after the collision, VA prime is equal to VB prime, which I'm just going to call V prime, and that's going to be question mark. Okay. The reason why I said VA prime equals VB prime is they said the cars lock together. This is what's going to be called a perfectly inelastic collision. Whenever two things collide and stick together, that's called a inelastic or perfectly inelastic collision. And in a particular reference frame, in a frame called the center of mass frame, for instance, the total kinetic energy goes to zero in such a collision. So that's why they call it an inelastic or perfectly inelastic collision. Now, the solution to this, you might think for a second, wait a second, there's a butt ton of forces actually acting on these trains. The weight of gravity is 9.8 times 10,000. That's a huge force. But there's a normal force acting on the train as well, in the upward direction, and that's going to be exactly equal in magnitude but opposite in direction. And of course, that means the summation of those two forces gives us zero, assuming the track is level. Now, in addition to that, you also are going to have air resistance, but these things are 10,000 kilograms. They're moving 8 meters per second. It's going to take a lot of wind before the train car feels any significant force from that, so we can ignore that. Uh, but what about those two train cars? They're going to slam into each other. Yes, they are, and that is a huge force. But since they slam into each other, that's part A bouncing off of part B or running into and sticking to part B. That's an internal force. So that would never, ever, ever go on the left hand side of Newton's second law. So we've now concluded that the net external force acting on the system is zero. Summation forces is equal to zero. Again, this is one dimension, but I put the vector back on there just to remind you that that's what we were comparing. But now I can say, therefore, P initial is equal to P final. And P initial is just MA VA plus MB VB, which VB, of course, because it was sitting still, is zero. So in this case, I get 10,000 kilograms times 8.0 meters per second plus zero. That gives me 80,000 kilograms meters per second is P initial. P final, on the other hand, is MA plus MB. I add those two together because they're now stuck to each other. And since I said VA prime equals VB prime equals just plain V prime, I'm going to write V prime there. And this is going to be equal to 20,000 kilograms times V prime. And that's our P final. So P initial equals P final just becomes 80,000 kilograms meters per second is equal to 20,000 kilograms times V prime. So V prime, I think, is obvious to you guys, 4.0 meters per second. Does that make sense? Anybody have any questions on that? Now, this is sort of like skimboarding, or if you've ever tried to like run beside like a skateboard and then jump on it, you'll notice that that is not necessarily a trivial skill. I mean, you got to be pretty athletic to begin with to try it. And if you're not, you'll quickly discover the laws of physics. Even though I quote unquote prided myself on being somewhat athletic, and I did do skimboarding for some time, as well as surfing and stuff like that. But every now and then you just screw up a little bit, and sure enough, if you don't match the speed of the skimboard just right, so that conservation of momentum when it kicks in doesn't bite you in the rear, then you're either going to fall forward and that hurts, or you're going to fall backwards and that hurts, or you're going to fall sideways and that hurts. Especially the older you get, it all hurts a lot worse. So that's really the problem if you've ever tried to jump on a moving skimboard or a moving skateboard or something like that. If you don't perfectly match the speed that it's supposed to have by conserving momentum, then what'll happen is you jumping on it will tend to slow it down a little bit, but because you weigh so much more than the skateboard, it's going to slow it down by a lot. So the skateboard more or less comes to a stop and you keep flying forward, or you go a little bit less than the skateboard speed and the skateboard takes off really fast and you fall back on your butt. But that's basically a ramification of conservation of momentum. Anybody have any
Um,
questions? Yeah.
yeah, how did we get to the 20,000 kilograms? We started with 10. I'm not sure where the other 10,000 came from.
So the other car was also 10,000 kilograms, but it was initially
Okay.
sitting still. Once they rammed into each other, they were stuck together, so they acted like one big 20,000 kilogram car.
All right. So, I mean, that caused it to be half as fast as it was before.
Exactly.
Okay.
Okay.
Thank you.
No problem. Next, we're going to do example 9.4. You can look in our module. You'll see I did some recoil calculations. I specifically did one for an AR-15, for instance, so you can look that up if you'd like. But I'm going to do one now. This is example 9.4. And this one they're saying rifle recoil. Calculate the recoil velocity of a 5.0 kilogram rifle that shoots a 0.020 kilogram bullet at a speed of 620 meters per second. So what we have is I'll write this as big M and little m. So big M is the mass of the rifle. That is 5.0 kilograms. Little m is the mass of the projectile, i.e. the bullet, which is 0.020 kilograms. Notice they were kind enough to go ahead and convert that to kilograms, but that's a 20-gram bullet, so that's a significant round. The actual muzzle velocity, I'll call V sub m, is equal to 620 meters per second. That's not an unreasonable velocity. The speed of sound is around 330 meters per second, but it's heavily dependent on air temperature. So it's not uncommon for you to run into 342 meters per second, stuff like that. But the main thing is, yeah, this is clearly faster than the speed of sound. So that's one of those things where the bullet hits you and then bam, you hear a bump because the bullet made it there before the sound did. The main thing is here, in this case, what we have is a rifle sitting perfectly still with a shell casing and the projectile itself and the gunpowder all sitting there, all perfectly still. So the initial momentum, Pi, is equal to 0. However, what happens when you pull the trigger is a little pin comes in and stabs the center of the back of the casing. That casing has gunpowder packed in it so tight that that little pin causes a rapid increase in pressure and therefore a rapid explosion. That explosion is inside of a casing that's not necessarily strong enough to hold it, but one of the things about designing a gun is you got to make the barrel strong enough to hold the explosion so that the explosion is directed in the direction that you want it to be, as opposed to just a random direction. Otherwise, you've got bits of shrapnel shooting off to the left and right, injuring your comrades. So they have to design the barrel to be thick enough so that when the explosion happens, the casing and the barrel are strong enough to keep the barrel from exploding outward, and all the explosive force goes forward to force the projectile out of the casing. When that happens, there will be a huge force. It's a force acting on the back of the shell. And that force, according to Newton's third law, is equal but oppositely directed to the force that's acting on the actual rifle. The good news is both of those forces we can't necessarily figure out, but they're both internal, so it doesn't matter. It's not going to ever appear on the left-hand side of Newton's second law. So the summation of the forces is equal to 0. Therefore, P initial is equal to P final. That's conservation of linear momentum. And P final can be written as the mass of the rifle times the velocity of recoil, which I'll call V sub RC, plus the mass of the bullet, basically, times the muzzle velocity. Now, P initial equals P final means 0 is equal to, that mass is 5.0 kilograms times V recoil plus 0.020 kilograms times 620 meters per second. Now, by calling that positive 620 meters per second, we're assuming, let's say, that the bullet is going to the right. That means anything with a positive velocity will be going to the right, and anything with a negative velocity will be going to the left, which I think you can see is clearly going to happen here. So what we ultimately get is the velocity of recoil is equal to the negative of, if I take the time to multiply 0.020 times 620, that is 12.4 kilograms meters per second, and I've got to divide that by 5.0 kilograms, and that gives me 2.48. Now that 4 was not a significant figure, so this 8 will not be a significant figure, and the result is a negative 2.48 meters per second is the velocity of the recoil. Anybody have any questions on that? Now, that is the velocity of the recoil. What that means is if you were, not that bright about or not that experienced about using rifles and you just haphazardly held the rifle like this, or like I saw a YouTube video of this woman looking over the butt of it with the butt right in front of her nose. Don't do that. That's not a good thing. Okay. If you did that, this would be what would happen. A 5 kilogram, notice that's about 11 pounds. A 5 kilogram object's going to be coming at you at 2.5 meters per second, and it's going to hit you right in the nose and knock the crap out of you. So ideally, what you want to do is rest that butt of that rifle on your shoulder, and you want to hold it sort of snug, and you want your shoulder to be able to sort of try to, if you will, absorb that force. Uh, it's not technically it's what they call eccentric motion or whatever, but the main thing is when that force goes, you want your shoulder to move back just the right amount where it stretches these muscles in your pecs, and allows the shoulder to go back a little bit, and but doesn't allow it to go back too far, and then you go forward. If you held it stiff, you'd actually still get a bruise, but if you allow it to caress it a little bit, sort of like catching a pop fly, you don't want to just hold your hand so rigid that it hits and bounces back out. You want to caress it and allow it to go down. If you do that, you'll be less likely to get bruised. Another point about this, though, if you've ever seen any of the old Dirty Harry movies, or Predator versus Alien, or Predator, or Terminator, or any of those kind of movies, you're probably at least used to seeing people like Clint Eastwood, who's a pretty good sized guy, especially for the Hollywood community. I think he's one of those guys that's actually 6 foot tall. He's not huge in terms of weight. He probably weighs 180 or something like that, which isn't that much for a 6 footer. But one of the big things he did as Dirty Harry is he would carry like this big 50 caliber handgun, and he would fire it, and he would hit somebody that's comparably sized, sometimes even bigger than him, and that bullet would hit the guy, and he would blow back and fall through the wall. Well, the laws of physics say that if that bullet did that to him, then that bullet was carrying enough momentum to do that to him. So that bullet had enough momentum to take, let's say, a 200-pound person and throw them through a wall at like 5 miles per hour or something like that. Well, if that's the case, then that bullet was carrying that much momentum when it left the rifle or the gun. And therefore, when Clint Eastwood fired the gun, that much momentum was created out of nothing, giving the bullet that much momentum. But guess what? The handgun had that much momentum too, but in the opposite direction, because initially the bullet, Clint Eastwood, and the handgun were all having zero velocity, so the initial momentum was zero. So if Clint Eastwood really did shoot that bullet that hit this guy that's slightly bigger than him and blow him through the wall, then by necessity that bullet would have to blow him through the wall as well. So that's not really going to happen. You can't do that. If you wanted that kind of event, then what you do is you'd take a really big gun and mount it on a Humvee or a tank or a destroyer or something like that, and then shoot something small. Then you could, actually, have all bits of people flying out this way and that way. But it's not going to happen with a person just holding a handgun. So hopefully that helps you understand a little bit about the physics of and where the physics goes wrong in those fun movies. Anybody have any questions on that one? I will. We only got about 5 minutes left, so I'm going to talk about this conceptual example 9.5, and we'll call it a day. It says an empty sled is sliding on a frictionless ice when Jeannie drops vertically from a tree down onto the sled. When she lands, does the sled speed up, slow down, or keep the same speed? So initially, the momentum is Jeannie sitting up top with zero velocity, the sled having some velocity and some mass. So m times v for the mass of the sled times the velocity of the sled is the initial momentum. Then what happens is Jeannie drops down, and she actually has momentum in the downward direction, but that's going to be more or less, quote unquote, absorbed by the sled and the normal force that the earth is applying to the sled. And since that force is actually perpendicular to the path, it's not going to speed up or slow down the actual sled to go left or right as a result of that. But what is going to happen is all of a sudden she's coming down, and now the momentum that we had for little m, the mass of the sled, times v, the velocity of the sled, now has to go into little m plus big M, the mass of Genie in parentheses, times the new velocity. Because Genie had no forward velocity, no velocity parallel or even anti-parallel to the velocity of the sled, then she's actually going to cause it to slow down. So yes, the actual sled will slow down by her falling onto it because she had no forward velocity when she hit the sled, and now the sled plus her is acting as uh, what we called a inelastic collision where they stuck together. Part B says later, Jeannie falls sideways off the sled. When she drops off, does the sled speed up, slow down, or keep the same speed? In that case, we're doing the same thing again. We now have a genie and a sled. They have a certain mass, little m plus big M, and they have a certain speed, this new velocity v prime. It's moving at some speed like this, and then all of a sudden, Genie falls off to the side. She's stealing some of that mass away, but she's also falling off with her own velocity. So she's taking that MV away with her as well, and going to the side. Now, the ground's going to slow her down and she'll come to a stop. So the sled will keep going, but the sled will definitely slow down because she's taking away some of the momentum by falling off of it sideways. If she had fallen off of it backwards, she'd probably be giving a little momentum to the sled. If she'd fell off forward, she'd probably be taking away more of the momentum of the sled. So that's what happens there. Anybody have any questions on that? All right, so I'm going to say last example was 9-5 conceptual. So you guys are free to go. Make sure you chat me your first and last name if you haven't done so already. Uh, Make sure you get your test scheduled with a proctor and get that done. You're welcome to come see me. Like I said, Wednesday, I'll be giving an exam. Technically, I'll be giving the exam at 12:30. So that's really the time you're supposed to come. But if you need to, I can do it during lab time, but it's not going to be an ideal situation. So you could be there as early as 9:30. It's going to be really messy and loud then, but if you come about 10:15, it'll be a lot quieter. And you're allowed an hour and a half. I can also accommodate you the following Wednesday, but again, the class time would be better, which would be either starting at 12:30, starting at 10:15, or starting possibly at 1:45. I'll wait here till the last person leaves in case anybody has any questions.
I had two questions about the chapter 8 homework.
Okay. Is there a particular one you want me to pull up? I can open it up so we can see, or you can share your screen, whichever one you'd like to do.
I don't know how to screen share.
Okay, no problem. I can
The
pull it up here.
one of them was part B for problem 8.31. Like
8.31, gotcha.
I
And it's the
tried,
homework, right? Not the conceptual.
yes. Yeah, the homework. I tr tried using it brings up using energy methods to figure out how far a ski will travel along a level. And for some reason, the numbers I got just would never
Gotcha.
work with it.
I'm reading it now. It says a ski starts from rest and slides down a 30-degree incline 70 meters long. This is this particular version. I think the numbers might change from one version to the next. Part A, if the coefficient of friction is 0.095, what is the sled speed at the base of the incline? Did you
That
remember that the
that I
normal
was able to
forces? Go ahead.
I was able to get it was zero point 0.8 on mine, but I managed to get the answer of 20 meters per second for 0.08
Gotcha.
for
Okay,
my
so
friction.
You basically, so you did manage to calculate the work done by friction, and then you set that equal to kinetic energy and solve for V.
Yes.
Gotcha.
Yeah, that one was easy, but it's just the second one is like I'm having trouble figuring out how far it's going to go from there once the slope
Gotcha.
ends, essentially.
So it says if the snow is level at the foot of the incline and has the same coefficient of friction, how far will the ski travel along the level? Use energy methods. So, did you remember to subtract out however much energy was stolen from it as a result of the friction down the incline? Because you went like a distance of 70 meters down the incline.
Uh, no, I don't think I did that.
That's probably why. So what you want to do is you found out your kinetic energy at the end. So now what you're going to do is set that kinetic energy, that new kinetic energy, 1/2 mv squared, where v is the final velocity that you got in part A. You want to set that
Uh,
equal to the coefficient of friction, which in this case is 0.095, times m times g, no sine 30 because this is horizontal, and then times L or D in this case, and solve for D.
wouldn't and I'm wouldn't I also multiply it by the coefficient of friction as well?
Yeah. I tried to say that first. It's mu times mg times L.
Okay. So just the kinetic energy times mass times gravity times
Yeah, but
coefficient of
don't
friction.
start with the initial kinetic energy. You want to start with the kinetic energy that it has at the end of the 70 meters. If the
Okay.
coefficient, the ski speed at the base of the incline. Yeah, so that'll give you the speed at the base. Then
Uh,
instead of that, you'll just do 1/2 mv squared equal to that quantity.
okay. I think the way I got it wasn't for A. I did cosine. I was doing not cosine. I did like the sine of the of I did the sine of the
The sine of the angle.
yeah, I did the sine of the angle multiplied by the coefficient, and that's how I got my answer.
Gotcha.
So I'd have to find the kinetic energy
A
and figure
ski
out.
starts
Okay.
from rest and slides down a 30-degree incline 70 meters long. Okay, so what you're looking at here is an incline that's 70 meters.
Yeah.
In this particular problem, the numbers are different for yours, of course, but this angle is 30 degrees. So that allows you to figure out what the height is because the sine of 30 degrees, which is equal to 1/2, is equal to opposite over
Right.
hypotenuse.
Right.
So you can see that h is going to be basically 35 meters.
Yes.
So now what you're going to say is mgh is equal to, well, if you wanted to do energy methods like I've been teaching you guys, then you could go ahead and say U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss, like this. In this
Okay.
case, we have MGH, which we just calculated the H, plus 0 is equal to, in this case, at the base of the incline is what they want to know the speed. So I'm still in part A just so I can use that number to show you part B. So
Okay.
the U final is going to be 0. The kinetic energy is going to be 1/2 mv final squared, meaning at the base, plus 0. And the energy loss is going to be a positive quantity, but it's going to be mu times mg times the sine, excuse me, times the cosine, because the normal force will be mg cosine theta,
Uh, yes.
and then times, in this case, the full 70 meters, which I'm going to call L.
Okay. And but we're using the normal force here, not the sine, because the sine
Yes.
is okay.
Yeah, because the normal force is what the friction is proportional to. So you've got to find the normal force, and then multiply that by mu to get the friction force. And the normal force is going to be the mg cosine theta, whereas the parallel force is the force going down the incline. That's the mg sine theta.
Okay.
Okay, so in this case, you can see that the mass actually cancels out, which is good because I don't remember giving us a mass. But
They
what we
didn't.
yeah. So what we now have is V final, one half
Wait,
V final squared. Go ahead.
there's mass twice on one side, but only once on the other.
That's
So
okay. We're
does it
dividing,
continue?
not subtracting.
All right.
So like that. And
Okay.
does that make sense?
Yes.
And this side's going to be GH minus mu G cosine theta times L, which I'll put over here so it doesn't get confused with what we're doing. So that actually gives me the ability to find the velocity at the end. You can see it's a factor of G, that sort of thing. But when you get to the other part and it says how far the ski will travel along the level ground, what you're going to do is say 1
Solve for L.
half mv final squared is going to be equal to, in this case, it's mu times mg, no sine or cosine, times d.
Okay.
And you'd solve for d that way.
All right.
Does that make sense?
Yes. And okay, yeah, I can figure it out from well, you step by step did, so yeah, I
Yeah,
hope I
yeah,
can
we'll
get
get
it.
most of it. I just didn't put the numbers in, but yeah, that should help you.
Yeah.
And
Yeah,
if
and
you use sine, you probably still get close enough to get the right answer. But cosine's what you were supposed to use if you worked out the triangle for the incline.
yeah. Okay. And for eight, the other one was 8.91, where the getting the angle was like easy, like super easy, but I'm
Hmm.
just having trouble with the tension.
Oh,
I think
gotcha.
that mainly
So
because like I think that's just had troubles with tension we were going over chapter five
Gotcha.
as well.
It
So
says a 51-kilogram student runs at 4 meters per second, grabs a hanging rope, and swings out over a lake. He releases the rope with his velocity is zero. What is the angle when he releases the rope? Okay. So in that case, you're setting, again, you're using conservation of energy methods. So right
okay,
here, I'm going to say U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss.
okay,
Uh, we're going to say the potential energy initial is zero because he's at ground level. His kinetic energy is 1 half mv squared. There's not going to be any work in. He is going to get a potential energy, and that potential energy is going to be m times g or times L minus L cosine theta, which I'm just remembering how to work that out from the pendulum that we did in class, where basically the distance from the ceiling down to the bottom of the path of the pendulum is L,
all
and
right,
when it moves up an angle theta, then this little part of it is L cosine theta. So if you take the L cosine theta from it, then you'll get just what's left, which is the height. So that's why I did mgl times or mg times L minus L cosine theta.
all
The
right.
kinetic energy is going to be zero there. The work out is going to be zero, and the E loss is going to be zero. So that should allow you to get. Notice the
The
masses cancel out.
the
One
kinetic
half.
energy is zero.
No, just the mass canceled out on that side. The kinetic energy at the top of the motion is zero because that's where they asked for what is the angle
Oh,
theta when he releases the rope. And he
okay,
said he releases the rope when the velocity is zero.
okay, okay.
That makes sense?
Yeah,
So now we have G times L times 1 minus cosine theta, and that gives you V squared over 2GL equals 1 minus cosine theta, or cosine theta is equal to 1 minus V squared over 2GL. So that should allow you to get the theta. And you said you actually were able to get the theta, right? But not the tension?
yes,
Okay.
right.
So that should give you the actual theta. Now, to get the tension, this is the angle theta. This is the length L, like that. And what we have is a force mg acting this way. We
Right.
also have this is the angle theta, so this one would be mg cosine theta, and this one would be mg sine theta, and we also have a tension acting on it, T. So if we imagined a coordinate system where this was like our x-axis and this was like our y-axis, then the summation forces in the y direction equals mass times acceleration in the y direction would give us T minus mg cosine theta is equal to, now remember, it's not zero. In order for this to go in a circle, he has to have an acceleration mv squared over r. So that's mv squared over L. Now, they asked for what is the tension in the rope just before he releases it. So in that case, the velocity was actually approaching zero there. So you might even have been able to say mg cosine theta.
That'll, hmm.
Let's see there. Yeah, it was
Uh,
plus v squared over 10.
well, if it stops, wouldn't velocity just be zero? So we can get rid of that.
Yes, that's what was trying to get me here. The velocity decreases, and comes to a zero right there at theta. And it's a matter of trying to figure out exactly what. Did they give us a mass on this one, by the way?
Yes, they
Okay,
gave us the
that would
mass of
hit.
the student.
Okay, well, that's the case. Then what you're going to do is say the tension is equal to M times G times. Oh, wait a second. Oh, did they ask for
Unless
the tension or the maximum tension?
the both part B is what the tension is before it releases it, and C is the maximum.
Oh, okay, gotcha. So, what is the tension in the rope just before he releases it? Two
Wouldn't the
times.
masses cancel out too?
Well, they can't with the T there. Uh, if the T was proportional to M, if there was a M times T, you could cancel it out, but you can't cancel it out right now. But what you do get is mg cosine
Oh, right, right, right.
theta
Yeah, you're right.
plus mv squared over L. And if we wanted that tension, it would be M times G. Oh, okay, gotcha.
Yeah. Okay, and then wait, but the velocity is zero, so wouldn't tension just be mass gravity cosine?
Yeah, that's what I'm thinking it would work out to be. Did you try that? Is that actually the right answer?
Yeah, I haven't
Let me
tried
try
that yet.
this
I was just
one.
let me try putting it in on my
I think
side.
that's the case here because in part B, he's releasing it right as the velocity reaches zero, in which case the only tension would be mg cosine theta. And his mass was 51 in my problem times 9.8
Huh?
times, did we find what the
Yeah, it
angle?
worked. Yeah, that worked.
Okay, gotcha. So that's it. It's just mg cosine theta when v equals zero.
And for maximum tension,
That's when
um,
the maximum tension occurs when the maximum velocity is occurring, and that
would
would be theta equals
right as he
zero.
starts.
Exactly.
Okay. All right. And since that's just essentially replacing the no, the cosine would be it would be cosine zero then because he just started running, right?
Exactly. His would be cosine zero, but you then have the mv squared over L that would come into play.
Okay. So yeah, okay. Yeah, okay.
All
I
right.
think I can do it. All right, thank you.
Good job. I hope that helps, Colin.
Yeah, it really helps.
No problem. Have a good
I
one, bud.
I managed to get my tests scheduled for Saturday, so
Oh,
I'll be
awesome.
able at the testing center.
Good deal. Well, good luck. Hope
Yep.
you do well, bud.
Yeah. Sorry, couldn't come to class directly, but with work, it's like
Yeah, I
I can
feel you.
only take so many days off, you know?
Yeah, I get it, man. Yes, that's the nature of community college. We're working while we're doing it.
Yeah.
Have a good one,
All
bud.
right. You too. Thank you.
Bye bye.